Good afternoon and welcome to the Jones Seminar talk for today. Thank you for making it in. It is my great pleasure to be hosting Dean Sanjay Raman today. Sanjay Raman is the Dean of the College of Engineering and a Professor of ECE at the University of Massachusetts, Amherst. Dean Raman joined UMass from Virginia Tech, where he was Associate Vice President for the VT National Capital Region, President and CEO of the VT Applied Research Corporation, and a tenured full professor in the Bradley Department of ECE. Dean Raman earned his bachelor's degree in EE from Georgia Tech and his doctorate in EE from the University of Michigan, Ann Arbor. Prior to his doctoral studies, he served as a nuclear-trained submarine officer in the U.S. Navy. He is a fellow of the IEEE, served on the steering committee of the DARPA Microsystems Exploratory Council, is a member of the Defense Science Board, and is co-general chair of the 2024 IEEE International Microwave Symposium. And that's going to be held in Washington, D.C. And with that, I'd like you to help me in welcoming our guest today, Dean Sanjay Raman.
Well, thank you, Kofi, so much, and thank you for inviting me to present in your Charles Jones Seminar series. A great honor. Had a great day today. Met a number of you. I think with all due respect to the faculty, my favorite part was lunch with the graduate students. That was a really, really great conversation, and you really just have a great bunch here, and I think really exciting research and environment. So today I will predominantly talk about the topic of 3D heterogeneous integration, progress and outlook. I'll try to keep it a little bit at the high level since there might be more diverse crowd from across engineering, but certainly there'll be some technical details here. But I would, I can't do this with this. I would just speak a little bit up front about the College of Engineering at UMass Amherst. So pretty young college. This is a little bit dated. This is from the fall, but we are celebrating our 75th anniversary as an accredited College of Engineering. College was founded in 1947. There was engineering degrees being granted prior to that, but the college really came on board in 1947, and it has been a quite innovative and important college of engineering. Some leading work in the area of wind energy, for example. Professor Bill Hieronymus, some people refer to as the father of wind energy, was a faculty member at UMass Amherst. We have a very strong wind energy center at the college. Led an engineering research center in collaborative and adaptive sensing of the atmosphere that has since graduated about 8 years ago. Ellen Ferraro here was one of the PhD students in the center. She's now vice president for the Raytheon Intelligence and Space organization or business unit. So really, really great college, great place to be. I keep pressing the forward button on this. Quick glance at the college. We're a modest-sized college. We have 5 departments, 7 undergraduate going on 8 undergraduate programs, 16 graduate programs, lots of other certificates and concentrations. About 3,000 students, 2,300 undergrad, 700 grad, 165 faculty, including non-tenure track lecturers and research faculty, about 135 tenure track faculty. And we do about $51.3 million, or more than $50 million of research annually. As I mentioned, strengths in microwave remote sensing and wind energy, but also in water resources and transportation, life sciences, cybersecurity, manufacturing. Some of the areas that we're really growing in, like most institutions in AI and autonomy and robotics, biomedical engineering. We have a pretty nascent biomedical engineering department that started about 5 years ago and is growing very quickly. Energy and sustainability, obviously a huge emphasis. We just launched a new material science and engineering program I'll mention a bit later, in quantum, as I had a few conversations about earlier, as an area of growth for us as well. In terms of our strategic priorities, obviously revolutionary research and helping solve interdisciplinary grand challenges, student experiential learning. We're very focused on growing our industry partnerships, particularly beyond just talent acquisition and recruiting into research and workforce development and a broader set of activities. And very important to us is advancing diversity, equity, inclusion, and belonging. Just a snapshot of our new faculty. We are growing quite quickly, but I'm especially proud of how we're diversifying our faculty. So over the last 4 years, we've doubled the percentage of women and underrepresented minority faculty. We have 27% women faculty in the college now, and 14% URM faculty in the college. So it's really fantastic to see all the talent coming from diverse communities. As I mentioned, DEIB is an incredibly strong, important focus for the college, and we're really happy to be making progress in terms of faculty. That being said, we still have a lot of work to do in this space. The pipeline and attracting more students from diverse communities into engineering and into STEM in general is an important focus for us, and I know that is for you as well. We're organizing into some research thematic areas. We have traditional departments, and so it is there are some traditional silos that we have to break down. But these are very similar to things that you all are focusing on here. But we also are trying to build all of this on a fabric of inclusive design, innovation and entrepreneurship, social justice, and as I mentioned, sustainability. As I mentioned a few minutes ago, we have launched a new program in material science and engineering. We don't have a department of material science and engineering. We have built what is called an interdisciplinary graduate program, so all 5 engineering departments, as well as chemistry and physics in the College of Natural Sciences, are part of this program. So the faculty live in their individual departments, but the students who join this program, which just launched this past year, and we're recruiting our initial cohort of students, will be getting a PhD or a master's degree in material science and engineering. So we're excited about this. The university has a very strong reputation in material science for many decades, although they did not have a specific material science and engineering program. So we're closing that gap, and I think there's a lot of great opportunities for students and faculty in the future. I'm also pleased to share with you that we were just awarded a $15 million University Department of Transportation University Transportation Center. It's the New England University Transportation Center, includes Norwich actually, MIT, University of Maine, University of New Hampshire, UConn, and a couple of community colleges, Bunker Hill Community College and Holyoke Community College. And really the focus of this transportation center is on safety and particularly equity and safety. So looking at community engagement, sensor networks, smart infrastructure, autonomous vehicle safety, really from a lens of equity and diverse populations. Another interesting initiative at the college I'm very excited about, I talked a bit with the graduate students at lunchtime about this as well. About a year and a half ago, we launched a very innovative partnership with the College of Nursing. So this is an endowed center, it's the Elaine Marie Center for Nursing and Engineering Innovation. The idea here really is for nurses who really on the front lines of healthcare, really see the problems and see the limitations and challenges with particular devices or particular systems on the front lines, to work directly with engineers in an innovation partnership. So this is not nurses as customers sort of getting handed a technology and finding the issues with it, but really working at the point of creation, the point of innovation on innovative solutions. It's really exciting. A number of different areas, medical robotics, IV smart pumps, are a number of the areas of focuses. A cool collaboration involves IV smart pumps in particular. As some of you may have heard, these pumps, when they're deployed, often do not deliver the doses that they're supposed to in real-world healthcare situations. Some of that is the way that they're hung, or the way that the piping or the tubing is routed, and so there's a collaboration between Karen Giuliano, who you see here, and a faculty member in mechanical engineering, Juan Jimenez, who's a fluid mechanics expert, to really study and understand how to make those IV smart pumps work more accurately. And in fact, they just launched a startup company to look at that area as well. And then we're also launching a new center in quantum information systems. This is an interdisciplinary effort between computer science, engineering, and physics in the College of Natural Sciences. We're at about 6-7 faculty right now, and we're planning to grow to about 8 to 10 faculty over the next couple of years. We have an active search in electrical and computer engineering for an experimentalist in quantum. And the idea is really to have a center of excellence that covers algorithms and theory and different types of devices. We have experts already in superconducting qubits and ion trap qubits, and we have a search both in physics and in electrical and computer engineering for device experimentalists this year as well. And we're also a core member of the NSF Engineering Research Center for Quantum Networks. One of our faculty, Joe Barnes, one of my colleagues in electrical and computer engineering, is actually on leave right now at Google and was a co-author on the quantum supremacy, quote-unquote quantum supremacy paper from a couple years ago. I think we can debate whether or not that was a demonstration of quantum supremacy or not. And a more recent paper on error control in quantum computers as well was just published about a month ago in Nature as well. So great group. I think we see a lot of opportunity in the quantum area. I think there might be some opportunities to collaborate here as well. So maybe I'll just take a couple of minutes and talk about my own research, which as a dean, I unfortunately don't do a whole lot of. So some of this is historical, but I am an RF microwave mixed signal integrated circuit designer, or at least my students are, and my former students are. We've done a lot of work in tunable microwave filters, work out in the upper left here on was published in JSSC a few years ago by Farouk Amin, who's one of my former students, in silicon germanium by CMOS. Some very interesting work in analog signal processing. So this on the upper right here was published in Transactions in Microwave Theory and Techniques by one of my former students, Shinwan Park. And this is a 3.5 gigasamples per second analog signal processor, FIR filter. So the idea here is to really do some of the signal processing in the RF domain prior to data conversions, is sort of get high speed and reasonable linearity before arriving at the A to D converter. So some interesting work and highly reconfigurable using a unique configurable capacitive DAC architecture. Probably the area where I'm working the most now is in quantum readout circuits. So we've done some work in reconfigurable cryogenic amplifiers for superconducting qubit readout. That's on the lower left here. And then some prior work in 3D millimeter wave, so-called wafer scale or reticle scale phase arrays. So this is some work from several years ago in collaboration with UC San Diego on a 60 gigahertz phased array, two-dimensional beam scanning, 50 plus degrees of scanning, with a sort of heterogeneous antenna layer that's electromagnetically coupled to the wafer. So the picture here with the coin is the actual 64 element phased array. And we actually demonstrated it also with 4 tiles coupled together to make a 256 element array. So some really, really interesting work there. That's really taken off. I haven't been as active in that area more recently, but the ability to make highly integrated RF systems and mixed signal systems in silicon is obviously a very exciting area, and I think it'll tie in more with what I'm going to talk about on 3D heterogeneous integration in a few minutes. I'll also mention, from a campus point of view, UMass is really trying to lead on sustainability and addressing the global climate challenge. So our chancellor announced last year on Earth Day, UMass Carbon Zero, which is an initiative to reach carbon neutrality for the campus by 2032. It's very aggressive. We'll see if we make it, but all of our new construction, new facilities are really aiming at achieving carbon neutrality for the campus. And that brings me to a new building project that we have. I was very, very impressed with your new engineering science and computer science building. We're kind of on the trajectory as well to bring on board a new building. This building is really thematically focused on clean energy, sustainability, energy transition. It'll be the headquarters for our Energy Transition Institute and Transportation Center, Wind Energy Center. Really a thematic interdisciplinary collaborative environment, so not the traditional departmental facility. So very excited that we're in the design phase. Just a couple kind of images of the new building. So it'll be labs, primarily research, but some classroom space, and we're expecting this to come online in the 2026 timeframe. So another activity that I've been pretty involved in, and I think you all are as well, is the CHIPS Act. So there's, as you probably have heard, quite a lot of money sloshing around the system to expand, to sort of onshore microelectronics manufacturing and really increase our national capabilities in that area. The most recent activity has been the so-called Microelectronics Commons, which is a Department of Defense program that's going to create regional hubs to focus on sort of lab to fab research to translation in the microelectronics area. So Massachusetts was in the lead on a very large regional proposal, including all the states in New England, multiple academic institutions, multiple universities to go after one of these regional hubs. The Northeast Microelectronics Hub would be, I think, the working title for this. And you guys are right there on the list, as we are, and so I hope we win this thing, and we'll have some opportunities to collaborate together. These are pretty large programs. I think it's still a little uncertain how the funding will flow to different university and industry participants in the program, but it's a pretty exciting era in microelectronics in the U.S. right now. It's a lot of opportunities, so we're looking forward to potentially working together on this. So that brings me to kind of the main part of my talk, which will focus on 3D and heterogeneous integration. So quite a bit of this is stuff from my days at DARPA, so you'll see a lot of DARPA slide logos that I'm borrowing here. So I think, as Kofi mentioned, I was there from 2007 to 2013 and led a number of programs in the microelectronics and integrated circuit design area. And I'll talk in a few minutes, but launched a pretty large program in heterogeneous integration. So we'll talk a bit about what that is and what the potential outlook for that is in moving forward. I think, interestingly, Gordon Moore, and of course, a week ago today, I think, Gordon Moore passed away. You all know Moore's Law. He sort of made this self-fulfilling prophecy of how microelectronics would scale, at least up until this point, which, I think everyone thinks it's going to end any moment, but science and engineering finds a way to keep extending Moore's Law, at least one way or the other. And certainly one way to continue to extend Moore's Law is in the third dimension, and we'll talk a little bit more about that. But I think it's interesting in this paper that Gordon Moore wrote in Proceedings of IEEE, he really envisioned this idea of heterogeneous integration and the integration of diverse components together in a single package or in a single system as being a way to extend capabilities and make them manufacturable and make them affordable. And so really, at the end of the day, we're continuing to follow Gordon Moore's vision here. And I'm going to talk about this in a bit more, a couple different definitions of what heterogeneous integration might mean and what 3D could mean. So some terminology, and this is my view of the world. You may hear other folks use these terms slightly differently, but in my view, there's sort of three big categories. The first is system in a package. So this is, you've got a package, you have multiple chips, they're interconnected together using sort of standard technologies, ball grid arrays, wire bonds. There can be some chip stacking, but fundamentally it's an assembly of microelectronic chips in a package. And together, those chips are performing some function. It's a system in a package. The sort of in-between space that we're really seeing a lot of activity in right now is what we call 2.5D integration. So this is some sort of a platform or a substrate that allows chips to be integrated. It's called an interposer or a redistribution layer. It can be fabricated in printed circuit board technology or other, silicon wafers. There's multiple different technologies that are being used for this. But these are individual dies that have specific functions. They could be different processors, they could be accelerators, et cetera, memory, and they have their own function, but then they're interconnected together in the system through this interposer layer. And so that's the kind of 2.5D integration piece. And then all the way on the right is three-dimensional integration. And here's where we are really talking about active tiers of semiconductor devices or semiconductor technologies that are stacked upon each other. Primarily the 3D ICs today outside of the memory world, because there's some really, really aggressive vertically stacked memories that are on the market now, hundreds of layers of memory into these sort of memory cubes. But for really, processor, active circuit types of architectures, traditionally they're really limited to two layers or two wafers that are sort of bonded together in a face-to-face sort of assembly. But there's a lot of opportunities to extend this using technology to greater levels of integration. So this is really the extreme direction that I think ultimately that we will go, that enables a lot of short interconnect distances between different processor tiers, really elegant architectures that are moving routing signals, routing information between different processing layers. And what I'm going to talk about probably mostly in this discussion is a more expansive definition of heterogeneous integration. So there's certainly heterogeneous integration in sort of a silicon perspective, which is different kinds of processors, heterogeneous processors, different technology nodes, memory, but all silicon technology. That's sort of one definition of heterogeneous integration. But the broader definition, and really where we were at DARPA when I started there and continuing on today, is a diverse group of semiconductor technologies, 3.5 technologies, MEMS technologies, different types of non-silicon memory technologies, photonics, integrated together in an intimate semiconductor platform. Sometimes we use the buzzword or the tagline when I was at DARPA, best junction for the function. So if a 3.5 transistor is your best device to do a certain thing, let's find a way to integrate it with silicon. If a 3.5 device is the best thing for photonics, let's try to find a way to integrate it with a silicon photonics platform. So that's kind of the idea, really the extreme definition of heterogeneous integration. And I'll make a further definition, more narrow definition of device-level heterogeneous integration. And this is where individual devices of different technologies can be accessed sort of as the designer would like to. So I can go between a gallium nitride transistor and a CMOS transistor, let's say, with this sort of intimate vertical interconnect distance. So this, I've sort of already said a lot of this already, but this is sort of my view of the 3D HI family tree. So on the top, you sort of have what you could do with pure silicon-based technologies. And on the bottom is heterogeneous technologies. So when we combine these two, we get these 3D HI integrated circuit platforms. So non-silicon memory integrated with silicon platforms, or lasers, as I mentioned, integrated with silicon photonics, or RF transistors integrated with CMOS. Antennas. non-silicon based or not non-silicon back end of the line based antenna feeds and antennas, imagers. So as I mentioned, I came on board at DARPA in sort of mid-2000s, 2007 timeframe, so sort of in the middle of the chart here. And I became involved in running some of the remnants of a 3D IC program, which was a silicon-based, multi-layer, wafer bonding-based program. And I also started managing a program called Cosmos, which was compound semiconductor materials on silicon. I'll talk a little bit about that in a few minutes. And then I went on to launch a larger portfolio of programs called DAHI, Diverse Accessible Heterogeneous Integration, and a component of that was EPHI, Electronic Photonic Heterogeneous Integration. And it was all about this best junction of the function idea. Let's put primarily 3-5 compound semiconductor transistors or other devices in intimate integration with silicon CMOS. And the programs have then continued since I left in 2013. Chips, I'll talk about in a few minutes down the road here. MOAB, which is a modular optical aperture building block program, which is really about building chip-scale LiDARs. In the EPHI program, we actually did one of the projects in the EPHI program was a chip-scale LiDAR program, and that went on to transition to this MOAB program. I'm not going to talk as much about that in this presentation. But let me back up just a second and talk a little bit about more from a mixed signal RF point of view, this idea of best junction function. So the plot here is showing, as you can see, transistor cutoff frequency, or FT, versus transistor density. And you can see the green curve here of silicon CMOS. So sort of at the 45 nanometer node, the analog performance, or the high frequency performance of those transistors sort of peaked. And digital CMOS, the objective is not really FT, right? The objective for digital CMOS really is density, right? So in order to get more and more transistors per micron or per millimeter squared, the high frequency performance of transistors we sort of sacrificed. And it's not terrible, right? You can still do a lot of RF things, pretty well. But if you really want really great RF performance, you want to go to millimeter wave or even maybe terahertz operation, CMOS has sort of run out of gas from that point of view. We could invest in that. We can certainly decide to try to develop better CMOS transistors that do that. But for the most part, that's not the goal of the manufacturing industry or the silicon CMOS industry as it stands, right? So the other technology that could potentially fill the gap here is silicon germanium BiCMOS. So this has been around for a while. In fact, in Europe, there was a lot of investment in trying to advance silicon germanium technology to get higher performance. And so a few years ago, DARPA decided to, hey, let's try to expand the performance of silicon germanium technology. So there's a program right now running. It's sort of in the last phase called T-Music, which is technology for mixed mode, ultra-scaled integrated circuits. And this program was really about trying to take, through silicon germanium integration, high-performance silicon germanium like HBTs and high-performance digital CMOS, so you get co-integration of really high-performance digital CMOS with high-performance RF components. And there was another technical area to really try to scale the transistors to the terahertz regime. So really, the idea was to try to do it all on a silicon platform and integrate with high-performance CMOS. So this was really the idea, even before T-Music ran, to have best junction for the function for RF and mixed signal applications. So this plot, and this is a little bit dated, so don't get too focused on where these data points are. This chart is probably 10 years old at this point. But really what I just want to communicate is the story here. So here we have Johnson figure of merit, which is the breakdown voltage in whatever device technology you're talking about, times the cutoff frequency of that technology. So you get a gigahertz volt axis, and then number of transistors, or we could have done transistor density here, but we did just number of transistors at that time. And so really the idea is to not only just push high-speed operation, but high-speed, high breakdown voltage operation. Gallium nitride obviously is top of the heap for that, but not very integratable with digital functionality. So the DAHI program, which is the successor to the Cosmos program, was really intended to combine multiple high-performance 3.5 RF and mixed signal transistors with high-performance digital CMOS. And you can imagine what the applications could be, right? I can put digital pre-distortion of an RF power amplifier with a lot of complexity, or I can do signal processing right at the aperture of a RF phased array radar. So a lot of opportunities to take advantage of the silicon control and digital performance and combine it with excellent RF and mixed signal performance. So this is kind of where we left things from, and I'll talk a little bit more about these in some later slides, but this is sort of a summary of the different technologies under the Cosmos program and the successor DAHI program. And we initially started with a couple of different approaches, 3 different approaches. A monolithic integration approach, so this is this Raytheon approach here. This is with this is in situ growth of indium phosphide HBTs in a silicon environment, right? So there are these basically wafers that were silicon substrates with, in this case, a germanium template, and then a silicon CMOS template. But the the indium phosphide HBTs were grown directly on this germanium interface to give us a decent lattice match, not perfect, but decent. Okay, and so indium phosphide transistors grown in situ, and then you build the CMOS afterwards in your CMOS program or fabrication flow. We also demonstrated this in sort of the latter parts of the Cosmos program with gallium nitride. It was a different approach there. There was a 111 silicon template, a regular 100 template, and then a 111 silicon template you could grow gallium nitride on, and then the CMOS devices above that. In the middle was an epitaxial liftoff approach. This was done at that time by HRL, so the epi was grown separately. It was separated from the epi wafer into little slivers, and those were then placed on top of the silicon, the already fabricated back end of the line of silicon process, and then transistors were fabricated indium phosphide transistors were fabricated in that case. And then there was the chiplet approach, and this is more really like the 2.5D integration technology that I mentioned earlier. This was primarily led by Northrop Grumman, and it really became sort of the baseline technology for the DAHI foundry program. And here, indium phosphide transistors, gallium nitride transistors, MEMS, were all built on top of, or built separately, and then essentially packaged or bonded in a high-density interconnect approach on a silicon CMOS wafer that was fabricated separately. So this is really kind of a 2.5D interposer that really has active CMOS, or it's an active interposer, and then different indium phosphide transistor, gallium nitride transistor, etc. And then we also moved forward a 3D IC approach, which is the wafer bonding approach, in this case with indium phosphide wafers and separately fabricated silicon CMOS wafers with a direct bond interface connection between those wafers. So this is probably the closest thing that we did with the integration of CMOS with indium phosphide in this case, or compound semiconductor technology in this case, with high density, intimate device-to-device interconnections. But as I mentioned, the main platform for the DAHI program was this essentially 2.5D kind of approach. 45 nanometer CMOS ultimately was the baseline CMOS technology, and then different types of gallium nitride technologies and indium phosphide technologies and MEMS technologies were able to be integrated, as I mentioned. One primary issue with this approach is thermal management, right? So any of these 3D architectures, thermal management is a really important issue that has to be considered in design, and It's usually the thing that is going to cause the most problems with this approach. So in addition to sort of electrical interconnects that are connecting your, in this case, gallium nitride hemp power transistor with different CMOS devices, is getting the heat out away from the gallium nitride transistor. So a whole bunch of these, what are called thermal interconnects or thermal heterogeneous interconnects, needed to be included. Which is a bit of an issue because you're wasting a lot of silicon space here in order to get those thermal hicks connected to the substrate. And that is, just going back 1 second, that is the advantage of this approach, because I can do my thermal management, if this were gallium nitride, say, I can do my thermal management down here directly onto this wafer and not have to waste all the silicon area. So there's a lot of trade-offs with these approaches. So we ran a lot of MPW runs. This sort of got taken over. I left DARPA around the time this program was just getting underway. Around the time we did this first MPW run, one of my colleagues, Dan Green, took the program over, took it forward through program completion, but ran a number of these MPW runs. Again, the foundry for the overall integration was Northrop Grumman, but the CMOS was Global Foundries 45 nanometer, and different partners were providing different types of different semiconductor technologies for the chiplets. And so this is a demonstration of a particular circuit that you could achieve by doing this. So again, Global Foundries 12 SOI, in this case, indium phosphide transistor from Northrop Grumman, GaN transistor from HRL, and this is a direct digital synthesizer, or a power DAC, if you will. And the idea is really to be able to convert a digital signal that you want to generate, convert it to an RF waveform, and directly amplify it at the output stage. So this high-speed DAC was implemented in, I think it was a current steering DAC in indium phosphide, and then the output transistor in the power stage was a set of gallium nitride transistors. And so literally you could have digital to high-power RF in a very efficient path using this heterogeneous integration approach. And just some data of this particular demonstration, 2019 timeframe, and you can hear this. You can see the power is really the big win here. Linearity is still a bit of an issue, mostly due to mismatches in that current steering DAC. But that could probably be improved, and certainly you could use silicon CMOS error correction, which is not really done to a high degree in this particular demonstration, but you could integrate a lot of error correction and digital signal processing in order to improve that linearity number and still be able to do high power and very small, high efficiency platforms. So really interesting. I think this is a success story for the program. Similarly, the program was able to demonstrate these really 3D ICs with indium phosphide and CMOS in a single stacked architecture or 3D IC architecture. Demonstrated in this case beamformers for phased array radars with high efficiency, high watt per square meter. Again, by using the high power, in this case indium phosphide transistor, and then using CMOS for a lot of the other functionalities of the chip. So again, you can make very small form factor, high efficiency, best junction to function sort of RF mixed signal circuitry. So some lessons learned. So the idea was really try to do this in a CMOS-like design flow. Design kits, just like you would design if you were a CMOS or silicon germanium by CMOS design kit, but now you have 3-5 transistors to pick from. You've got potentially MEMS to pick from, whatever you put in that design kit. So design enablement and simulation was a huge issue with this program, getting that right. Being able to do verification, design rule checking across these multiple different technologies. So a lot of effort went into that. I would say, still a lot of work to be done in design tools and in verification for these kinds of heterogeneous systems. But that being said, it showed that we could, kind of design like a CMOS designer, do this best junction for the function thing, and demonstrate some high performance RF and mixed signal. But yield was a big issue, and at the end of the day, manufacturing is where the rubber meets the road, right? So if you can't yield these things, nobody can really use them in the real world, and you can't make money on them. So I think it's a little bit, you have to be a little bit cautious when talking about yield in an R&D program like this, because you're just not running enough volume, right? So if we were truly running CMOS-like volumes of these, heterogeneous processes, we could have gotten the yield up, or the program could have gotten the yield up. It's just there's not enough runs, not enough volume. So, but at the end of the day, that really matters a lot. Planarization, huge issue, right? So Silicon World, they know this, they've learned this. There's a huge amount of technology innovation went into chemical mechanical polish and planarization. That was not fully developed in this program. That there's work to be done there. And there's fan-out issues because, as you saw from that gallium nitride transistor, pretty big, right? And I need all this thermal management stuff. That can be a problem. Okay, so the chiplet approach can be good. It's simpler. From a yield point of view, that was probably the highest yielding approach for the program. But from a thermal management and stacking point of view, area usage point of view, not probably the best opportunity. So, where are we headed? So we did all this stuff, I would say, from 2005 to, sort of 2019, 2020 timeframe, this, kind of, decade and a half of work on heterogeneous integration, integrating 3.5s. I didn't talk a lot about the photonics, but there was a lot of work in photonic integration with silicon photonics and 3.5s, LiDAR on a chip, et cetera. Around, I'd say, late 20-teens, this idea really caught on in, I would say, the silicon world, right? And really from a silicon point of view, but heterogeneous integration is really now the direction that the commercial industry is going for very complex, high-performance, particularly digital, but also mixed signal systems. So a lot of effort on 2.5D integration, interposer technologies, different kinds of processor integration technologies. And the other thing that's happening, which will really help this, is standards, right? So there's a universal chiplet standard now that you can, if everyone is using the same interface standard, and this is obviously from a digital point of view, a bunch of different companies can design different chiplets to do different things, and they can all integrate them together in a single platform. And there can be this sort of mixing and matching, again, kind of the best junction for the function idea, but here we're really talking about digital accelerators, AI, FPGAs, memory, that we can interconnect together in a unified platform. So, really exciting work. The industry has really taken this idea of 2.5D certainly integration, and 3D integration, I think, is around the corner as well. DARPA took forward, again, this broader definition of heterogeneous integration, which includes 3.5s and silicon and so forth, and started a program called CHIPS, which is still going on, which is, in this case, common heterogeneous integration IP reuse. So again, this idea of having chiplets of different kinds, having a common interface standard. Here, the Intel Advanced Interface Bus standard is what is being used in the program. And a lot of really interesting, in this case, an FPGA with RF A to D converters coming directly to the FPGA, and then optical interface on the other side. So you can imagine, phased array radars or RF base stations that have, RF coming in, a lot of signal processing, linearization, encryption, decryption, et cetera, happening on this FPGA, and then optical on the other side, very compact, potentially very high performance. And honestly, the glue here is standards, right? So whether this UCIe thing takes off or this Intel bus takes off, whatever it is, that will lead to a lot of innovation in the industry on these different chiplets and allow them to be integrated together into really cool systems. So how am I doing for time? I should hurry up and finish, right? Let me just make a couple real quick comments. So one of the areas where heterogeneous integration, I think, is also poised to make an impact is in AI. Okay, so I think a lot of you I think some of you I heard are working sort of in this space of artificial intelligence, machine learning processors, and so forth. So you're probably aware that there is opportunities with so-called compute and memory, right? So if I look at speed or operations per second versus power, and there are these fiducials of TOPS per watt, the most efficient architecture that we're aware of right now is compute and memory. So, and this is sort of one paper from ISSCC a few years ago. I can't even read it. I think it's 357 TOPS per watt demonstrated in a compute and memory architecture. So there's really opportunities of combining in sort of a 3D heterogeneous integration architecture memory and doing compute and memory adjacent to CMOS processors. So this is some work from my colleague Chengfei Zhao from UMass Amherst. So he's working in the area of memristors, which are really resistive RAM memories, if you want to think about it that way. This is the cover slide on my cover slide. Some of the first demonstrations of 3D integration of memristors on top of a CMOS architecture. And they've taken this forward, I'm going to go quickly here, taken this forward for image processing at the aperture, in this case video image processing, using multi-layer 3D neural networks that are formed from these memristors or resistive RAM architectures. Again, Nature Electronics from 2020, so this is a 3D memristor array that's been integrated on top of the CMOS chip. And the application is this DARPA program, which is called FENCE, which is Fast Event Neuromorphic Computing Engine, I think is the name of the program. That program is still going on, but the idea is to have a focal plane array and whatever technology, through some 3.5 technology, imager technology, and place a neuromorphic computing engine right behind that array to make some decisions about what's happening in that scene and decide whether or not to move information off of the sensor or not, right? So one of the big issues is the communications bandwidth. If I send all my video to the cloud, that's a lot of communications bandwidth. But if I could make some decisions right at the edge about whether or not to send that information, that would certainly save me communications resources in sort of a resource-constrained environment. But also from the point of view of latency, if I have an autonomous vehicle or a drone or autonomous air vehicle that is flying around or driving around, and we want it to make decisions quickly, making decisions at the edge quickly is really critical to those kinds of systems. So this idea of doing some sort of compute and memory, edge processing, AI, if you will, at the edge behind the sensor, I think is a key area. I think there's going to be a lot of development and exciting opportunities in this area for research as well. Okay, so maybe I'll skip this. This is sort of, I've talked about some of this already. So DARPA has a current program that is underway right now. It's called the Next Generation. I think this is my second to last slide. Next Generation Microelectronics Manufacturing. So this is really about, again, trying to do what we did in DAHI, but really at scale, and do a lot of volume, get the yield out, fix the yield problems, and create a national sort of pilot line for 3D heterogeneous integration for multiple technologies, 3.5 technologies, lasers, MEMS, etc. So this program is kind of in a study phase right now, and they're really going to be soliciting proposals to really build one of these facilities for sort of the national level. And this is sort of part of the whole CHIPS Act story to kind of pull that thread. But a big piece of this is going to be that design enablement, design kits, design tools. Multi-physics design tools are going to be a big issue here because you need to understand thermal, you need to understand optical, you need to understand the electrical performance, interconnects, electromagnetics potentially. So a lot of work to be done here, a lot of interesting, I think, research problems in both design, computer-aided design tools, and certainly manufacturing and materials. So this is just sort of kind of where we are with this whole CHIPS Act thing. So this purple thing in the middle here, NSTC and NAPMP, is the Department of Commerce funding. There's $39 billion. There's $11 billion that's going to support the standing up of those facilities. There's $2 billion in this microelectronics commons that we're all partnered together on, and DARPA is building this NGMM capability under that program for 3D-HI. So tons of stuff happening in the next few years in microelectronics manufacturing, design, and 3D and heterogeneous integration. So really exciting time to be in this world. I'll leave you with this slide, which I think is a potential future direction, which I would say is the idea, in a sense, like that epitaxial liftoff thing I showed you that HRL was doing a while back. Can we integrate high performance, high quality semiconductor materials, non-silicon semiconductor materials in the silicon back end of the line, right? So this is the idea here, more, there's more than more. Can we build these devices with 2D materials in the back end of the line, have this integration thing, but don't have to do chiplets, don't have to bond wafers together, grow these materials in situ. This is a paper from Nature Communications in March of 2022. This is a recent idea. We'll see what happens. DARPA is looking at this. I think there's some potential future programs coming in this area. So I think it's a good time to be in microelectronics manufacturing and design. And with that, I'll get off the stage. And happy to take questions.